Hey everyone, and welcome to another episode of Space Science with Python. Today we are in session number 9 of our NEO project. And as a small recap, in our last session we created some sky maps of the NEO. So what we did, we created with matplotlib a sky map here in this ITOF projection. We plotted the sun position in ecliptic coordinates and also the opposition points, so 180 degrees away from the sun, and then plotted the NEOs and took a first look where these objects are. And we used pandas to do some filtering, and I was wondering, well, it's a little bit too not very intuitive usage to just simply change all the time all the parameters. So I was thinking to add a small session in between, and this is today's session where we are creating an interactive tool to show or to plot the NEOs here in the sky map. And to create an interactive tool, we are using ipywidgets. And ipywidgets, here's the link. It's a very nice tooling where you can add some interactive elements into your Jupyter-Notebook environment. So for example, you can add sliders like this one here, or a float slider. You can also, where is it? Yeah, some rangers, for example. So if you would like to have some interval between two values, you can also do some loading bars, you can add tags and so on. So there are a lot of possibilities also with buttons and with also date time pickers. And there are also a lot of possibilities to format these things, so adding colors, changing font sizes and so on. So there is some high level of customizability. Today we are just introducing this kind of things in our sky map, and there's also small homework for you, because I was thinking that of course I would like to present you and tell you how things can be done in Python and in Jupyter-Notebook, and especially in the space science context, but maybe one or two small challenges between the videos would be also quite good for you to have a task to work on the notebooks and do some stuff. So for the interactive tooling, I would suggest now to dive into the code. So everything is in notebook number 09. It is basically a copy of 07 and 08, so it just adds more and more cells because it relies on the computations that have been done in the previous sessions. And this is now cell number 23, where we are simply executing the ipywidgets import. And we are also adding a new column, which is the angular distance between the NEO and the sun. So if you take a look here, we have the sun position and we have here somewhere a NEO, and we are computing the angular distance between these two objects. The reason is, I would say, a little bit hacky, because what we want to do is we want to create some kind of tooling for our telescope operator, or if you have a telescope at home for yourself, where we would like to get the positions of the NEOs that are interesting and also visible, so adjusting the apparent magnitude. But of course, we can't observe during daylight, right? It would damage our telescope. And also even during dusk and dawn, when the night sky is a little bit illuminated already, even this illumination is enough to damage a telescope, especially some high quality or high-end telescopes. So instead of now plotting a horizon where we have to add geographic coordinates and so on, we will stay with our steady state solution. Also, we will not change the daytime, but we will compute the angular distance. So for example, you can say, okay, I'm not interested in objects that are within a radius of, let's say, 50 degrees or 40 degrees. Yeah, so we will add this as a filtering so that we can ignore this area that is basically invisible for our telescope. So this is now here done in cell number 24, and we use for this computation a spice function called vsep. Here, vsep is simply a function that computes the angular separation, so the angular distance, the separation between two vectors in 3 dimensions. Input is quite simple, the first vector and the second vector, and then it returns the values in radians. So we have to take the Earth to NEO possession vector and the Earth to Sun possession vector, and throw it into the function and then convert it with NumPy into degrees. Cell number 25. We are now creating some widgets, and I created 1, 2, 3, 4, 5 widgets, but the very first one is, let's say, a dead one. Let's start with the second to the last one. So we have a drop-down menu where you can choose between the different Neo classes like Armor, Apollo, Aten, Atira, so the inner Earth objects, the ones that are not within the definition range, and also everything. So we will name it Neo class. We will also add a widget, a selection range slider. So we have like 2 sliders, yeah, as we have seen it here. Let me go back to the slider. Yeah, this one here, where we can adjust the apparent magnitude. So we say, okay, we are only interested into NEOs that have a apparent magnitude of at least, let's say here in this case, 3 magnitudes and up to 8, for example. So this is what we define here, and we define it in a range from 5 to 31 meg. I think this is really sufficient, and our index starting points so that we have some initial values and simply call it apparent magnitude. We do the same thing also for the absolute magnitude, ranging from 9 to 35. So these are like the values where our NEOs are, also with the same index value. So these are like the initial values. And then finally, we also add the angular distance between the sun and the NEO. And we use the integer slider. So it's like the slider here, but yeah, like only with one selection button. And yeah, we have like discrete values. So I just said, okay, let's put it into a range from 0 to 60 degrees and in 1 degree steps. So this is now I call it sun distance. Now the very first thing is, let's say, your homework assignment. I would suggest that you get some kind of homework assignments, and I would suggest that you create some kind of solution. I know do not have a lot of subscribers, and I know some of you are regularly coming back and taking a look at the videos and do the coding and so on. But my suggestion would be the following, that if somebody of you would like to do the homework, do it, yeah, and make maybe a pull request. And we call then this pull request, you can name it however you like. I have to think about the structure. And I would choose one particular homework assignment, and then I would present it maybe in a video. Yeah, if I get something, of course, if you guys are interested at all into making pull requests. Maybe I will throw a video in between on how to make a pull request or how the structure should look like, because there should be some guidelines for you to contribute. And in this case, it's a date time picker. So there will be a date time picker where you can select the date time or only a date, and the time is then only midnight, and it's disabled. So you can change something, but the sun position or neo positions, they will not change. This is your homework assignment, to add this functionality into the next cell that we are going now, namely cell 26. I wouldn't suggest to go really into detail. I will just execute it just in a second. But the most important thing is here, we have this function that is being called with this ipywidgets interactive function. We throw in the function name, the plot sky map, and also then the different widgets. And the different widgets are the input of our function, like the date, the neo class, apparent magnitude, and so on. And then we have here our filtering. So we have our NEO data frame, and then we create what I just called filtered NEODF. For example, here based on the classes, based on the apparent and absolute magnitude, and then also how I call it the angular distance. And then afterwards, we simply plot everything with the same settings, so almost same settings like as last time, and this time with smaller fonts, because I would like also to plot the number of visible NEOs in the title. I would suggest let's execute this small cell, and we have here the sky map with only one NEO visible, so with the default settings. We have here, as I said, the daytime picker, but you see it's dead. It doesn't work. So try to add some kind of functionality here to see whether you can add some time dependency also in the plot. Now let's go through the plots a little bit. We can, I would suggest to increase the apparent magnitude a little bit to also visualize the fainter ones. And you see with every step, more and more objects appear. The same applies also for the absolute magnitude. It becomes really, really crowded, so there is no transparency or so. The dots are just plotted. And now if we increase here the sun distance, you will see that, whoops, more and more objects vanish. Of course, due to the projection, this is not a perfect circle. The circle is morphed into this ITOF projection. So don't be confused that we don't have a perfect circle here. This is simply due to the projection. Now we can go a little bit through and let's see whether these data make sense. I would suggest the sun distance increasing to 0. And for example, let's take a look at the Arteras, so the inner Earth objects. And you see they're very close to the sun. So if we have like an angle of, I would say, 30 degrees or even 45, then we have only 7 NEOs visible in this range. Now we can take a look. The parent magnitude, let's say 26. Yeah, so they are within our observation range, but very close to the sun, as you see. So within a range of 45 degrees or beyond 45 degrees, but it's still quite close. If we increase it maybe 50 degrees, one disappears, and 60 degrees, only 3 NEOs are left. So these are quite difficult objects to observe and also to detect. So there are probably tons more of objects, so a lot of NEOs within the Earth orbit. But as you can see here, playing around with the sliders, it's quite difficult to find them. We can also plot all objects. This is, of course, again, very, very crowded. So let's say 60 degrees, and this is our region, let's say, where we can detect our objects or observe them. And you see also the concentration around the ecliptic plane. We can also, yes, we see also the opposition effect here. So maybe not in this case, but for example, let's take a look at the armor. And let's say, okay, we would like to see only the brighter objects, yeah, and also maybe an absolute magnitude, let's say larger objects. And then you see more and more objects vanish, and then within a certain range, if we increase now the sun distance here, you see that, yeah, you can guess it a little bit. It increases, or you see more objects here directly on the other direction of the sun. So if we also now take a look only at the fainter objects, so these are very bright objects, but let's say only the faint objects, yeah, so small and faint, you will see that these objects, they gather around the opposition point, yeah. So this is like one of the effects of the opposition effect that we were describing in our previous sessions. So now this is a video about this interactivity tool. You can now play around a little bit, again, with this small assignment of creating your date time picker. And the question is also, how do we proceed with the projects, right? I mean, we will not create 100 videos about NEO. So I would like to show you a small outlook, what we do in the next sessions, or how we will also conclude the project. So in our next videos, we will make some kind of NEO simulation. So for example, asking the question, okay, how long does it take to, e.g., detect 80% of all known NEOs? Yeah. So we see this sky map here. So let's say we have an NEO here. It's visible. Of course, we can't observe the entire night sky the whole time. So we can say, okay, let's take a small circle around, I don't know, the opposition point. Yeah. Let's say with a radius of 20 degrees, so we simplify things, and then we see how long does it take to observe all or 80% of all NEOs or 50% of all NEOs within the circle within a certain apparent magnitude range, right? So like let's say brighter than 26 magnitudes, yeah, something like that. We will also do the same thing also with some NEO population model, because this here is not a model, these are actual values. So of course there is a certain bias, yeah, a bias in maybe orbital elements and so on. But we have a lot of NEO models, like the model from Botke or so, where we have then artificial NEOs with an hopefully unbiased absolute magnitude distribution and unbiased orbital element distribution, and we can use it to maybe determine some kind of observation strategy, or answering the same question, like, for example, Are there certain NEOs within a certain absolute magnitude range and also orbital element range that are rather difficult to observe? Or are there certain regions for objects within an orbital element range that are, where do they appear? Are there, let's say, regions of interest or for better or better detectability? So this is something we will do with some NEO model. And this is also freely available data, so I also prepared these things partially. And then at the very end, we will increase the complexity to the maximum. We will model a telescope, its optics, and a camera system. So at the end, we will have an interactive tool, not only with apparent magnitude, but we will replace it with with the telescope settings, like for example, telescope focal length, the diameter of the main mirror, the reflectance of the mirror, the camera system, like for example, the exposure time and the pixel size, the signal to noise ratios and all these things. So we will model everything step by step so that at the end of the day, we'll have a very huge interactive tool where we can then, put in our settings to see what kind of NEO strategy is the most, the best observing strategy to find as many NEOs per night as possible. We will also add some geographic attributes, like for example, also the horizon and so on. So we'll take a position on Earth. I don't know which one, maybe at the Atacama Desert, so a very dark region, and then work with values there. Yeah, so this is like the task we will do in the next couple of weeks. And I hope you guys enjoyed this interactive plotting and you will play around a little bit. And then we will also take a look at the telescopes and so on. And then, after concluding this project, we will then jump to another project. But there is still some stuff to do. I hope you will do the homework assignment. If you're not submitting a pull request, it doesn't matter. At least maybe try it for yourself. And I'm looking forward to your feedback and the comments. And until next time.